All right, last lesson in 17, video E. Let's do one last example with two proportions. So, an internet study claims that whilst 27% of males expect to be financially prepared for retirement, only 18% of sampled females express that opinion. If the survey was administered to 200 people of each gender, could you conclude that more men expect to be financially ready for retirement than women? So let's check this out. First, we need to run a hypothesis test for the difference in attitudes. Is that 9% difference there between the 27 and the 18%? Is that discrepancy a true pattern prevalent in both populations in general, or is it just natural sample-to-sample variation? We are going to run the test using a 0.05 significance level. So we'll start by summarizing the data. We'll set up our hypotheses, look at our conditions, and carry on. So first from the data. Let's look at the males first. It says that we sampled 200 males and that 27% of them felt that they would be okay for retirement. If 27% of the 200 felt like they would be okay, 27% of 200, that meant that 54 of them answered that way. For the females, again, sampled 200 females, it was 18%. And if we take 18% of the 200, 36 of the women in the sample in the survey said that they thought that they would be financially okay. All right, let's set up our hypotheses. So that's what our sample data told us. Remember, nothing from that sample data belongs in these hypotheses. You could have set up the hypotheses before you even collected the data. This time we have two proportions we'd like to see. Are the proportions the same? That will be the assumption. We're looking for evidence in this case of what? Let's see. We need to run a hypothesis test for the difference in attitudes. Nowhere does it say that we're looking to see if more men feel like they'll be okay. It's a difference in attitudes. So right there, because that says difference, I'm going to look for a difference here. So that comes from the context of the problem. I think I have some space here to check our conditions. You either are comfortable with how you're going to be set up for retirement or you're not, so our variable's categorical. Sort of a check. Doesn't really talk a whole lot about where the samples came from, but we can assume that the samples are unbiased at a minimum. Our sample sizes were 200. That's certainly less than 10% of the entire population of males and females. So both, put both. Both of our samples are less than 10% of their respective populations. And then the success-failure condition. For males, we've got 54 successes, so we have like 140 some failures. For females, it was 36. You'll have 164 failures. So the success-failure condition is met for both groups. 10 plus successes and failures. You know, if you were to do this problem and find out there were only 6 females out of the 200, you'd have to go increase your sample size, but we're okay. All right, so after you have written down your hypotheses, checked your conditions, you should know what's coming next. Got to compute that test statistic, get the p-value and make our decision here. So let me erase, make some room. So our test statistic, and actually before I even do the test statistic, there is one little tiny thing else that I'll mention here. You need that pooled p-hat value. What if we pooled our two samples together? What would the overall percentage be? So I will just do one calculation here first. There were 54 successes from the males, 36 from the females. We sampled 200 of each. If you look at them together, this is a pooled proportion of 0.225. So you're going to need that for your test statistic. So the rest of this you already have. So that Z test statistic, we look at the difference of our two proportions in the numerator. So we'll take the males, 27% minus the females, 18%, just written as decimals. And then we're going to divide by that big square root, where we use that pooled p-hat. So I'll take the pooled p-hat times 1 minus that. We divide by the number of males that we sampled, was 200. And then we do the same thing over here. This time we divide by the number of females that we sampled. Just happens in this one that the sample sizes were the same, so that's another 200 there. You ought to be able to put this in your calculator and get this. Watch parentheses. You need a set of parentheses around that numerator. You want to be taking the square root of that entire part there. Pause, make sure you can get this. Your Z test statistic, when you do this, you ought to get 2.155. So that's what you ought to get from here. That difference of 9% in our two samples, that's 2.155 standard errors away from 0. So that kind of gives us a glimpse of what we might find out when we look at the p-value next. So, just like usual, take that test statistic, draw the normal curve, the standard normal curve to get your p-value. Zeros in the middle, this is Z. 2.155 is getting to be further out toward the tails here. And then you have it above. I've erased it, but you've got your alternative hypothesis there. That's what you look at to determine where you shade. It was a not equal to, which meant that this is going to be a two-tailed test. So I'm going to shade not only this tail, I'm going to come down here to negative 2.155, and I'm going to shade that tail as well. And you know then that the p-value is the total area of those two tails. You should be able to use StatCrunch to get the area of either tail, and you know that the area of the other tail is going to be identical. And if you add up both of those together, you should get a p-value of 0.0312. And I will just make a note to remind you that p-value is the area of the two tails together. So make sure you've taken them both. So that is this with that. Okay. After your test statistic and your p-value, we have left stating our decision and then writing out a conclusion sentence. So this p-value is on the small side. It's not incredibly small, but is it small enough for this problem? We are given a significance level for this one, so we can compare that to alpha, and our p-value of 0.0312 is smaller than 0.05. So when your p-value is small, we'll reject the null hypothesis. So I'll write that up and then we'll write our conclusion. So our decision that p-value like a pet peeve of mine. Don't just say reject. Say what you're rejecting. Which hypothesis are you rejecting? So don't forget that. That's important. So we're going to reject the null hypothesis, which means we are finding evidence in favor of that alternative. And we'll say what we're finding evidence in favor for in our conclusion here. So we were looking to see if we had a difference in the proportion of men and women who feel comfortable about being prepared for retirement. And the null hypothesis was that they were the same. The alternative was not that men feel more comfortable than women. It was, is there a difference? So we can't conclude that men feel more comfortable than women. All we can state is that we did find evidence that there's a difference in how men and women feel. So we did find evidence that there is a difference in the proportion of men and women who feel comfortable or prepared for retirement. Okay, and that concludes the hypothesis testing part of this problem. Then, just like the last one we did, there's a part B. We're going to construct a confidence interval, and we're going to support the results of this hypothesis test with a confidence interval. So let's get to that. All right, so support your conclusion with a 95% confidence interval for the true difference in the proportion of men and women who feel confident to retire comfortably, and will interpret. So just a note, we want to be 95% confident, right? If you think about the standard normal curve, we want to be 95% confident. That will leave an area in each tail of 0.025. That's better. This does equate to what we just did, because what we just did was a two-tailed test where alpha, the total of the two tails, was 0.05. So a 95% confidence interval is equivalent to the test that we just did. I'll write up the formula. You ought to try this. We're going to look at that best guess, the difference of our two proportions. Plus and minus the margin of error, which starts with a z-score. That'll be 1.96, right? Times that standard error. And you have all those numbers. You know what this is because we're 95% confident. So make sure you can get this. Pause this. Work this out. Try this yourself. If all you do is watch and you don't try it yourself, this isn't going to stick. So do this yourself. All right, now hopefully you've unpaused and you've done this yourself. You should verify that you get a confidence interval where the lower limit here is 0.00863, and the upper limit of this confidence interval is 0.17137. Make sure you can get that. Let's think about this confidence interval. If you sort of think about these as percentages, multiply these by 100, this goes from 0.86%, not quite 1%, up to 17%. And this was a confidence interval for the difference in proportions of men versus women. And we didn't emphasize this with this one, but you could even put these in if you wanted to. Notice they are both positive, right? And we were looking for males to equal females versus was there a difference? If there was a difference, which we found, then that difference would all be of the same sign. Our interval would not contain 0. And so, I'll write this up in a second, but we're 95% confident that this interval contains the true difference in those proportions. And just as a note, since that whole entire interval is positive, that would indicate that it does look like there is a difference. It actually looks like, since it's positive, that more males are feeling comfortable than females. Let's see what I have room to write from here. So we are 95% confident that our interval there, and I'll write this as percentages since this is easier to relate to, that goes from 0.863% to 17.13%. Contains the true difference in the proportion of men and women that feel comfortable about retirement. If you remember the order that we did the subtraction, oh, it's right here. We looked at males minus females. And so since the differences here are always positive, this implies here that actually the percentage of males that feel comfortable about retirement is more than the percentage of females. That entire interval is above 0. The entire interval is positive. The only way you're going to get that difference to be positive is if this proportion for males is higher than females. All right, that is it for lesson 17. Thanks for watching.